topic of today's video is the twin prime counting equation. This is another original equation derived by me, Sergio Fernandez. I always start my videos by actually showing the equation, which is going to be the topic of the video I'm making. This is the equation which I'm going to be talking about today. What is a twin prime number counting equation? Well, twin prime number counting equation, as the name implies, is an equation that tells you how many twin primes there are in a given range. A twin prime number is a number that is either 2 less or 2 more than another prime number. So why is this equation important? There is a famous conjugate called the Twin Prime Conjecture, also known as the Klutz prime twin conjecture in number theory, that asserts that there's an infinitely many number of twin primes. In order to prove that, I thought a good place to start is actually to know how many primes there are in a given range, and then we could build on that equation. This equation does just that. It tells you how many twin primes there are in a given range. Also, besides the twin prime conjecture, there are other conjectures out there based around the twin prime. So this has some useful values in trying to solve those other equations. Okay, so these are the building blocks that I'm going to use to make this equation. The first equation is I'm going to use is my twin prime test equation. And the other equation I'm going to use is my max value equation. Okay, this is the part of the equation, the part of the video where I explained how I arrived at the equation. I'm going to start off with my twin prime check equation. Now, I'm not really going to explain in detail how I got this equation because I have another video for that. I'll put the link to this video at the bottom. But basically, this equation tells you which x's are twin primes. If an x solves for this equation, it's a twin prime. Okay, so this equation is my starting point. What it really does is I take another equation which I created, which is my number of factors equation, this equation, and I look at this point x equals 2, which is my prime line point, x equals 2, because by definition a prime number is a number that has 2 factors, one in itself. So this is my factors equation. This point is my x equals 2 factors, which defines all the prime numbers. I'm interested in twin primes only. So I'm interested in looking at this line, and I look at every number, but just looking at this point because twin prime means it has a prime and then 2 points away has another prime. This point also is a twin prime because it has a prime here and 2 points away it has another prime. This one as well is a twin prime, a prime here, 2 points away, another prime, and this guy. The way I actually do this is by actually summing this point and then 2 points away I add it together, and if it's a twin prime it should be 2 plus 2 should be 4. So what I'm actually doing is taking my originally number of factors equation, adding it a point x and x plus 2, and I get this new equation up here, and when x equals 4 I get my twin primes. So actually I modify the equation to be this new equation, and at the x equals point line these guys are my twin primes. Great. So I've modified the equation. Now I could identify which are the twin primes. I want to do a trick where I could sum up the twin primes here and ignore these guys up here. So my original equation had it at x equals 4. I want to start simplifying things a little bit. So if I take the original equation, let me show you up here. In this equation I start at n equals 1, right? And I go to infinity or to x. I don't really have to add infinity, because everything after x will be 0. I have another video that explains that. But if I start off at 1, my twin primes will fall at the x equals 4. But if I adjust this equation to 2, then I get rid of this one twice, the first point twice, essentially bringing down this equation, bringing it down to the x equals 2 line from x equals 4, because I'm excluding 2 points. This simplifies things a little bit for me. Again, I have other videos explaining in details what this is all about, so I'll probably put the link down at the videos. And I'm going a little bit quick in this explanation, since I've already done this explanation many times before. I actually did this explanation for the prime number itself instead of the twin prime, but it's a very similar logic. So I adjusted my equation, which tells me which are the twin primes, to x equals 2 instead of x equals 4. So if I look at this line, all the points where this solves are twin prime numbers. Now remember, this is a twin prime counting function, so I want to take a range, like this one is from 1 to 25, and I want to add how many twin primes there are. So I want to add this point, 1, 2, 3, and 4. I had a technique that I've used in the past where I could keep these points here and ignoring this point, basically making this other point 0. If I do 1 over the equation, 1 over the equation will kind of flip these points here to be between 0 and 1, and we'll keep this 1 at 1. Well, not really 1 over it. Since this is 2, I have to do 2 over it. So 2 over this function, for the points where it is 2, it'll bring it down to 1. And these guys, for the numbers that are bigger than 2, it'll bring it down to to a number between 0 and 1. So that's what I do here. I take the original equation, I take 2 over the original equation. That gives me this new function. This function pretty much just kind of flips everything over, and now it has a nice little property that at the points where it's a twin prime, it's at 1, and at the points where it's not a twin prime, it's a number between 0 and 1. Now I could do my raised to the power of infinity technique. Raising 1 to higher and higher powers will always remain 1. 1 times 1 is 1. 1 times 1 times 1 times 1 is 1. So multiplying this many times is always 1. However, multiplying these numbers many times by itself will tend to bring it down to 0. So like a half by a half becomes a quarter. A quarter, a half by half by half by half is pretty much a quarter by a quarter becomes an eighth. So these things will start going down to 0 as I raise it to infinity, and this will remain 1. So I modify my equation to raise it to infinity. I don't really have to go to infinity. Actually, this equation tends to give me what I want rather quickly. I could just raising it squared or raising it to the 10th power pretty much is good enough. Raising it to the 20th power is pretty much almost perfect, so you don't have to go to infinity. Here, I think I squared it. So this was the original equation. It's about a little bit. It's a little bit more than a half here, a little bit less than a half here. Here, it's pretty much about a quarter here, and who knows what number, but it's pretty much bringing it down when I square it. And if I raise it to the 10th power, it's virtually 0. So if you look at the graph now, at the points where it's a twin prime, it remains 1. At the other points, it brought it down to basically 0. So now I could do my little trick of just simply adding everything up. So if I add all the points of this function, for 2, I get a 0. For 3, I get the numbers are off down here. For 3, I get a 1, which is 1. For 4, 0. For 5, I get a 1, which is 2. So pretty much I add this. So pretty much between 0 or 1 and 25, I get 1, 2, 3, 4 twin primes. Everything else is squared. So this is where I get my final equation. My final equation is I take the twin prime check equation. I take 2 and divide it by that number. That'll do the reciprocal. I raise it to infinity. You really don't have to raise it to infinity. I think 10 is pretty much close enough. 20 is like almost perfect. And then I sum up all the equations. That gives me my twin prime counting function. I probably went a little bit quickly to the explanation just because I gave this a very similar explanation for prime number counting. So I'm probably going to put the prime number equation down there. It's almost identical explanation, only it does it for prime numbers. But now that I have the equation, I could just check for bigger range. Like for here, it checks between 1 and 100, and between 1 and 100, it says that there are 1, 2, 3, 4, 5, 6, 7, 8 twin primes. Between 1 and 200, it says that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 twin primes. And between 1 and 200, it says that there are 21 twin primes. So that's pretty much it. I think I probably went a little bit too quickly to this explanation. That's because I did an explanation for the prime count equation, which is basically identical to this one. So if you want to go and see my prime counting equation, how I arrived at it, it's pretty much identical to this one, and it'll probably give you a slower, more detailed explanation. All the steps is the same. The only difference is my starting point. Instead of starting with my twin prime check equation, I start with my prime check equation. That's the only difference. So that's it. These are the steps. That's how I get my twin prime counting equation. I'm gonna try to start putting little spreadsheets at the bottom so you could download it and see that the equations test out. I'm gonna start doing it for all my videos. And again, you could ask any questions, and I'll be happy to reply. I didn't explain in detail this part because I already did another video, and I think again I went too quickly to this explanation because this explanation is virtually identical to the prime counting explanation. This is a twin prime counting. This is a prime count. This is the other one is a prime counting, but the explanations are virtually identical. Okay, thank you. The next video I plan to make is not math related, but computer related. The next video I plan to make is a video explaining an algorithm on how to do face recognition using histograms.